The flavor of this talk is a little bit different, I think, than some of the other talks. Maybe that's welcome, maybe that's not, sorry. I run a group at NREL called the Scalable Algorithms Modeling and Simulation Group. And the flavor of this talk is more like we use AMReX for a whole bunch of different things at the lab. And I want to kind of run through some of those as examples. And because I know myself, I'm going to get right up to the edge. And so I want to make sure to give you the punchline before I walk out. So we try to exploit in our group the ready-made supported algorithmic components of AMReX for a wide variety of different physics problems. We are moving to a mode where instead of simulating a handful of cases when we have a capability, we want to use the HPC as a provider of high quality training data for outer loop applications, so building surrogate models that represent high fidelity data. And just as a general thing, AMReX enables quick access to state-of-the-art solvers, performance portability, and excellent support and algorithmic reusability that we make use of. So at NREL, there's a lot of problems where we're designing, analyzing, controlling, or managing complex energy systems. In the Computing Sciences Center, we support the development analysis of and scale up of the models that are kind of underlying these studies. We look at a wide variety of energy systems, from fuel and material synthesis to power generation and distribution to industrial processing and associated materials design. And so just in our group, there's probably 50 or 60 different projects. Here's a small sampling to essentially demonstrate the breadth of applications. So the first one, secure, robust load management strategies for integrated power systems. That's what that little icon in the upper right is supposed to indicate, sort of a hierarchical building control. Intelligent control of autonomous experimental material synthesis. So the picture in the middle that's very small there is material synthesis lab, and the pictures on the bottom are comparing diagnostics extracted from the experiment and diagnostics computed from the simulation. And it's supposed to suggest to you that we actually use the simulation to control the experiment and decide what the next points ought to be, as they're trying to optimize in this case, the smoothness of the surface they're creating. We do a lot of work with the synthesis people. Bio-derived synthesized fuels, looking at the impact of thermodynamic and chemical properties of these bio-derived fuels and how they perform in combustors for industrial heating and propulsion applications. At an atomistic level, we look at corrosion and degradation in energy systems. This can involve batteries, but also phase change materials and thermochemical materials used for storing energy. And then we do quite a bit of work in biofuels area, both from a feedstock side, we're managing and processing the feedstock, to bioreactor design and performance stuff. So that's a pretty broad range of things. So when we develop models for these systems, we have access to a bunch of different resources and expertise in the group to manage that. Depending on the complexity and the performance we need for the simulations, we'll either pull something off the shelf, like a commercial tool like ANSYS Fluent or Converge, or for atomistic simulations, it'll be LAMMPS or VASP or something. We also have a fair expertise with OpenFOAM, throwing together some different multi-physics simulators on a real quick, on a week or two time scale. And then we have some problems where we do kind of fully homegrown models. And for those, AMReX is the key tool that we use to put these together. So those are typically in places where we have kind of moderate complexity, but we need the models to scale and be performance portable. So here's a list of, I literally asked my group to provide for me the AMReX based codes that they gave, and this is just a subset, and I probably won't be able to get through those, but it's to give you a sense that we throw together a lot of these tools. Some of them are long-term development projects, like the first two. Some of them are kind of multi-year, and some of them are even like 6-month development applications. So it's a different flavor than focusing on a single problem for 15 or 20 years and making deep and significant progress with parallelization and all this stuff. We really are on a short time scale to try to deliver some kind of insight to the applications folks. So in all those application codes, this is sort of the menu of components that we kind of slap together for these codes. Of course, almost always we need to depend on performance portability, being able to run on GPUs or CPUs. We often need structured grid adaptive mesh refinement, but not always. We often need embedded boundary for complex geometries, but not always. And we typically put together these applications by pulling standard operators for advection, for diffusion, for reaction, and for coupling all those things using the provided second order explicit and implicit schemes like ppm and Godunov and those things. And if the flow is constrained like incompressible or combusting low speed flows, then we use the projection schemes that are provided with the library. A lot of the algorithms which I'll show are based on kind of particle representations. Some of those particle representations interact a lot with the mesh, and so we make use of AMRex's capabilities there to couple the two. We make a lot of use out of ultra high performance I/O, including data compression, when we're making animations and such. And then when needed, we couple to sundials and hyper to do complex linear solves or to do complex reaction integrations. But in general, we interact a lot with the AMReX team as we're putting these things together and run into problems. So I'll try to go through some of these codes to give you a flavor of what they look like. The first one is kind of one of the longer standing codes. It was developed under the Exascale Computing Project called Pele. It's a suite of combustion codes for compressible and low Mach number flows. It was developed originally to do detailed chemistry, detailed transport, multi-phase liquid spray fuels, soot, radiation, essentially DNS calculations. And it was a multi-institutional collaborative development project that was led out of Sandia, but included folks at NREL, folks at Berkeley, a couple of people at Oak Ridge, and one guy at Argonne. The result of that effort is an open source cross-platform tool. The little QR code will take you to that location. Essentially, we showed that we made this set of tools to run efficiently on all of Frontier and all of Aurora to do very large scale calculations. And these pictures are designed to give you a sense of the sort of variety of cases that we've run over the years, from kind of older RDE flames to one right now. This picture here, if you can see my mouse, I don't know, is a combustor that is an experimental facility at Georgia Tech burning sustainable aviation fuels. Some of these other pictures are spray flames, plasma-assisted combustion at the bottom here, and a cool U-turn burner that stabilizes premixed flames from flashback that we interacted with some folks in Norway on. After the development of ECP stopped about 1.5 years ago, the complexity of the systems we were looking at kept increasing. The number of species for the combustion models and the need to account for things like soot production kept creeping into more and more complicated problems. So in addition, the problems are getting bigger and bigger to where we can no longer resolve things with DNS. So now we've added models for large eddy simulation in the code and the ability to handle various reduced order manifold, reduced order models for complex chemistry. One of the places that we get a lot of interaction or a lot of funding over the years is through this HPC for EI, where we interact with industry for these short 1 to 2 year projects. They're kind of all over the map, and they come to us wanting to make use of HPC resources without really any skills to do that. And we provide for them tools that they could use after a year to look at their systems. There's a couple of examples of those. Again, these are like 1 to 2 year projects. We worked on oxycombustion of supercritical CO2 with a company called 8 Rivers, thermal energy project with Element 16, a multi-phase steel project with a company called Danieli, and creating CO2 snow with Carbon America to extract carbon from exhaust gases. Marc HDF will talk a little bit about AMR Wind, which is a big code that we support in the context of wind turbines and such, but we also use that code for a lot of other atmospheric flows. In this example, Shashank and my group has added diagnostics around a CSP plant with these heliostat mirrors and wanted to know what happens when they're subject to large wind events. And so this is some calculations he's done to estimate what the torques are on the devices that hold these heliostats up, how the wind events impact the bending of the pylons and the tilt of the mirrors, and ultimately the focus ability for these mirrors to focus on the energy storage device that usually in a tower. I thought that was kind of cool. In the bio area, Hari and my group has spent a fair amount of time developing a number of different codes for transport and chemistry models and biocatalysis. This example here called Mesoflow it uses immersed boundaries coupled with a compressible reacting flow solver to look at the homogeneous and surface chemistry that goes on during these catalytic processes. The geometry of these little devices, of these little particles, are taken from XCT scans, and so it's a fairly generalized geometry. The pictures on the upper right are looking at flow and chemical processes and things like trees, various bio feedstock. And then, so this code is used to look at things like conjugate heat transfer, chemistry, and in applications that include biomass conversion, catalytic upgrading, and even iron ore reduction. So another code that we have that was put together fairly quickly is called eChem AMR, and it looks at the performance of batteries, essentially. These changing of geometry and the changing of reactions that happen on the surface of both the cathode and the anode, and how they interact with the electrolyte between them. This uses an immersed interface method for handling the boundaries between the solid and the electrolyte, and is used for looking at lithium batteries and also some CO2 reduction problems. This one's kind of neat. This is a DEM code written by Nick Deek, postdoc in the group. He uses something called bonded spheres to create kind of semi-realistic shapes of different biomass feedstocks, and does calculations to see how to make them flow through hoppers and what happens when they get stuck. And you can apply these forcings to unclog them, basically. It's probably an application of AMReX tools that most people haven't seen, so that was kind of a neat thing. In a similar approach, the material point method is used to not only look at free surface calculations, it's kind of a fun problem, but also looking at what happens when you have a water purification membrane under extremely high pressure, where the large scale porosity is removed by getting squished. So these are geometries that are taken from electron microscopes and used to represent the pore structure, and then we can calculate how the forces can compress those away, and then look and see how the membrane performs what it's designed to, its filtration processes. Another one is when they're manufacturing battery electrodes, they compress them between rollers, and we want to see how that affects the material structure. So material point method is a really flexible tool for that. Another related numerical approach is the Lattice-Boltzmann method, and we're just learning about that. So we have a brand new implementation of that. And again, it'll be used for something like batteries, and it's particularly useful when the solids are swelling and shrinking and the flow is changing between the solid particles over time. Let me see here. Is there like a movie going on next door? Changing gears a little bit, there's this talk, it's vaguely related to the adaptive mesh and algorithm refinement stuff that John Bell talked about a little bit earlier. This is a study looking at what happens when you mix two gas flows above the surface that you want to create a perovskite layer by layer. And to do that simulation, you'd have to compute the mixing and the dynamics of the gas and the volume, and then you have to do some complicated, very expensive calculation for how the surface grows in response to that. Conceptually, that makes perfect sense. The problem is that the atomistic simulations are way more expensive than the fluid dynamics. And so it's a very imbalanced and not really feasible calculation. But what we've done is wrap this coupling with something called adaptive computing, which is a generalized tool we've developed in the group to internally manage the training of surrogate models to represent complex physics. So one of the things that it does is it monitors the difference between the surrogate's predictions and the detailed simulations. And if you try to access a point where the model suggests that your error is above a threshold, then it could launch a bunch of jobs to generate training data to improve the surrogate automatically in that area. It makes use of a cloud-based queuing system to run these jobs, and it sort of automatically maintains the prediction accuracy below a specified threshold. I'm not going to say much about this except that it'll be talked about a little bit later today. Our collaborators in Korea have coupled the combustion code Pele-LM with interface reconstruction library in order to simulate the sort of atomization of a liquid jet going into a gaseous domain, ultimately as part of a spray fueling calculation. So he'll talk about that in more detail. And then finally, Marc HDF has been working on AMReX for parallel discrete event simulation, which is really cool and yet another very different application of the AMReX technology. And this is event-driven dynamics. So you imagine you have a logical entity that is sort of monitoring some other signal and every now and again gets the signal to do something that's going to affect its neighbors. How do you try to program something like that on a GPU in parallel when all these guys are working independently? And he's come up with a strategy that sort of optimistically moves things forward but keeps track of how to back up the system when you need to back up and take it and take account of a neighbor's activity. This is in development, but really cool stuff actually. And then finally, we are starting to wrap a lot of these tools in the Python AMReX framework so that we can develop them even faster. And so Nick Weimer here has created a driver around our Pele-LMX code. It's not playing. I guess I gotta leave my mouse there. And it was a pretty simple thing to do given all the tools that come with Pele or with the AMReX capabilities. We're able to create a graphical interface, create a input function control, a couple of menus and things to fire off a case and then to plot the results. It's a nice framework to do analysis within like a Jupyter notebook, and we can start to wrap a lot of the codes that we've developed here. My summary again is that we are making, I think, really good use of an amazing framework, and we sort of attack these as quick one-off calculations that we're developing an expertise on, and we're kind of pulling in all the pieces from the AMReX framework and kind of assembling them all in unique ways and solving a lot of problems at the lab doing it. That's it.
Maybe time for a few questions while the speakers change over.
Hi. The last you showed the Python driver, what is exposed from Python? I mean, like, is Python just saying run the code, or do you have access to the data that's lived in the plot file?
So Python's providing a GUI to manage the inputs. Python is aware of where the outputs are going, and it will capture the outputs and create an animation while the calculation's going. You can use it to set up the geometries, the boundary conditions, kind of anything you do to set up and run the code and look at the results all in separate motion.
So you are tapping into the data. So the data that flows is actually in the plot file.
Yeah, so there
That's the kind of data you're having access to.
it's being written to a plot file, but the GUI is reading the plot file and displaying the data.